Hi, in this video I will talk about isomerism in alkenes. We are going to talk mainly about the two types of isomers, which are constitutional isomers and stereoisomers or geometrical isomers. Constitutional or structural isomers, as we mentioned in the previous videos, that constitutional isomers or structural isomers are those isomers that have the same molecular formula but they differ in their atomic connectivity. So the atoms are connected in different ways. And in alkenes, just moving the double bond from one position to the other is enough to make the compounds constitutional or structural isomers. For example, in this case, this is C4H8, so this is a structure of 1-butene. However, if I just move the double bond to be between carbons and 2 and 3, so this is 2-butene, the relationship between this compound, structure 1 and structure 2, is structural isomers. Why? Because they have different bond connectivities. If you try to just look at the structure here, for example, this is a CH2, and next to it there is a CH, and so on, whereas this one here is a CH3, and next to it there is a CH. So we have different bond connectivities. Atoms are connected in different ways. That's why the relationship between these two structures is that they are constitutional isomers. I can also draw one more structure where we make the chain shorter and then put the branch here, and this is going to be 2-methyl 1-propene. So 2-methyl 1-propene, 2-butene, or 1-butene, all these are considered as structural or constitutional isomers because they have the same molecular formula, but their structure or their bond connectivity looks different. Also, we can try to draw the isomers of C5H10. So this is going to be on the first isomer. The second one could be just moving the double bond to this position here. So this is 1-pentene. If I move the double bond, this is going to be 2-pentene. Now, just moving double bond one more time to this position will give you the same isomer. That's why it's not going to be a different compound. What we are going to do is we are going to make the chain shorter. So now we have 4 carbons, and we will put a branch here. And this is going to be 2-methyl 1-butene. Also, if I moved the branch 1 carbon away, this is going to be 3-methyl 1-butene. And we can also move the double bond to this position in between and then put the branch here, and this is going to be 2-methyl 2-butene. So there are several ways to draw this compound. And again, the relationship between all these structures is that they are constitutional isomers or structural isomers. Geometrical isomers or cis-trans isomers, they differ in the relative orientation of a group in space. So the cis one is the one which has branches on the same side, whereas trans is the one which has branches at opposite sides. First of all, when can we use cis and trans isomers? We can only use them if we have similar groups at the double bonded carbons. So if there is no similar or common group between the double bonded carbons, as we will see, we cannot use cis-trans. We have to use something else. It's called the easy system. So let's go for this right now. Geometrical isomers exist only if each carbon is bonded to two different groups. That's the first point that we should be familiar with. Sometimes you will be asked whether those compounds have cis-trans or easy isomers or not. How do you know this? You have to look at each carbon. So just look at the double bond. This is the first carbon of the double bond. Look at A and B. If A and B are different, and at the second carbon, if C and D are different, then in this case, yes, we do have cis-trans isomers, or later on we will talk about ZE isomers. Okay, so those should be different. A should be different than B, and C should be different than D, which means that each carbon should have two different groups. If the carbon is bonded to two similar groups, then there are no cis-trans isomers. Let's take some examples here. For example, starting with this compound. So the question now is, do we have cis-trans isomers or not? Look at just the carbon which have a double bond, so those two only. Starting with this carbon here, what are the branches which are associated? Since nothing is drawn here, so this means that we have two hydrogens. Since this carbon is bonded to two similar elements which are hydrogen, this means that in this compound there is no cis-trans isomerism. Done. Move on to the second compound. Again, we will focus on this carbon here and this carbon here. So at this carbon, what are the branches? The first branch is this one, which is a methyl group. The second one is not drawn, so definitely this is a hydrogen. Now this and this are different, so we're fine. Let's move on to the second carbon. Second carbon is holding or is bonded to CH3 from this side, and it's bonded to this group from this side. Again, this group is different than this group. So again, the right carbon has different groups. In this case, yes, we do have cis-trans isomers. We will later on tell you whether this is cis or trans. Let's move on to the third example. Starting with this carbon here. Just look at this carbon. It's bonded to this group and this group. Those are actually the same. Same group, so there is no cis-trans isomerism. Let's move to this example here. Starting with this carbon. This is the first group. Where is the second group? It's a hydrogen. Well, those two are different, so we're fine. Let's move on to the second carbon now. Again, the first branch is this one. The second branch is a hydrogen. Those two are different. Since this carbon is bonded to two different groups and this carbon is bonded to two different groups, yes, we do have cis-trans isomers. One more example. Moving to this point here. This one is bonded to. This is branch 1 and the second branch is a hydrogen. Those are different, so this is fine. Second carbon here, this one. This is the first branch and the second branch is a hydrogen. Again, those two are different, so we're fine. Yes, we have cis-trans isomers here. Last example here, starting with this carbon here. First branch is a CH3, second branch is a propyl, so those are different, so we're fine. Second carbon, this is a CH3, this is another group, so those are different, so fine. So yes, we do have cis-trans isomers. So the point is that look at each carbon alone. Does it have two different groups? Yes. Move to the second carbon. Does it have two different groups? Yes. If both are yes, if both have different groups, then we have cis-trans isomers. Otherwise, no. The answer is no. We don't have cis-trans or even easy isomers. Okay. Now, someone might get confused between cis-trans isomerism and conformational isomers, and they say, why don't you just why don't we just look at cis-trans isomers in the same way as we look at conformational isomers, so that they can rotate? In fact, in double bonds, if you have a single bond, then this free rotation is allowed. And because this free rotation is allowed, yes, there is no difference. A and C are on the same side. When they rotate, they will be on opposite side. However, when we have double bonds, this rotation is not allowed. So rotation around double bonds is not allowed. That's why if your compound has A and C on the same side, it's impossible for this compound to rotate to put A and C at opposite sides. So this is not possible. And that's why we talk about geometrical isomers when we have alkenes, whereas we don't talk about geometrical isomers when we have alkanes, unless they are cycloalkanes. So whenever rotation is not possible, then we can talk about geometrical isomers, cis and trans isomers. And these orbitals basically explain why is the rotation not allowed, because if you try to rotate the double bond, then you are going to make those two orbitals perpendicular to each other, which means that you are breaking this pi bond, and that's why this rotation is not allowed. Now, let's go back to the same examples and try to determine whether these are actually cis and trans isomers. So cis isomers are those isomers that have a common group on the same side. For example, if I have H here and H here, and then I could have, for example, CH3 here and CH3 here. Now, to know whether a compound is cis or trans, you have to find a group at the first carbon or the left carbon and a group at the second carbon which are similar to each other. And then you have to compare the positions of those two groups. For example, in this case, I could choose hydrogen here and hydrogen here. Okay, those are two similar groups at two adjacent carbons. Since those two hydrogens are on the same side, this compound is called cis. Now, someone might decide to choose, for example, the CH3 groups. Fine. CH3, CH3, again, since they are on the same side, this is cis. However, if let's say the compound was drawn in this way, actually this should be a hydrogen. Now when I try to compare the similar groups, so we have hydrogen on this side, hydrogen on this side. So see, one of them is above the double bond, the second one is below the double bond. In this case, this is called trans. Again, if you try to compare CH3 and CH3, those again will be on the opposite side. Now sometimes you may have only one common group. For example, let's say you were given this compound and you are asked if this is a cis or trans isomer. First of all, you have to draw the missing groups. So the missing groups are a hydrogen here and a hydrogen here. Now, step 2, try to find a common group between the left and the right carbons. Well, the only common group between the left and right carbons is the hydrogen, because this group which is here and this one is here are different. So again, look at the hydrogens. Those are at opposite sides. If you are a little bit confused whether they are on the same side or opposite side, just put a pencil or pen here, or draw a line which crosses the double bond. Your groups are, one of them is above the double bond, the second one is below the double bond, so this is trans. Now sometimes you may not have hydrogens. For example, let's say I gave you this compound. Okay. Again, I ask if this is a cis or a trans compound. So step 1, you are looking at this carbon here and at this carbon here, and you are trying to find a group which is common between both carbons. Well, for example, CH3, we don't have a CH3 at this carbon here, so a CH3 cannot be chosen. Whereas if I looked at this carbon here, this is a branch which has two carbons, and I have a similar branch on the other side. So those are the similar branches. If I compare them, those are on the same side. So if this is my double bond, those are both above the double bond. So this is what? This is cis. Let's take one more example. For example, let's say you were given this. No matter how complicated the structure is, let's say you were given this and you were asked, is this a trans or cis compound? Again, trying to find something common between left and right carbons, starting with those 2 points here. The common group between the left and right carbons is actually this one, because the other ones have different number of carbons. This one has a 3 and this one has 4. So those are not common. Again, the common group, one of them is below the double bond, the other one is above the double bond. So those are at opposite sides, and this is trans. If the compounds didn't have a common group, Then we have to use the other system, which is called the easy system, which we're going to be in the next video.